Okay, this is Phil 385, 585, Reason and Choice, Lecture Week 8, Part 2. So thank you to Robert for doing the lectures up until now. As Robert mentioned, I'm going to be taking over the lecturing for the last few weeks. And I'm Sandy Boucher, by the way, the unit coordinator. So this is the second half of the Week 8 lecture. So last time, Robert talked about the landmark work in game theory, the book from the 1940s by von Neumann and Morgenstern that really kicked off the research program of game theory. And he talked about the general methodological program outlined in that book. Von Neumann and Morgenstern suggested that there are 4 stages that a science or a new scientific theory has to go through. This is their attempt to kind of vindicate the scientific status or potential scientific status of game theory and more generally science of economics, which they saw as being in a very, primitive or rudimentary state, but they saw every chance of it developing into what we might call a mature science, much the way that other established sciences such as physics and chemistry had. So they suggested that there were 4 stages typically in such a development. Firstly, preliminary stage. Secondly, stage of corroborating applications. Thirdly, the stage of more advanced applications. And fourthly, the stage of predictions. Now, roughly, we can think of the first stage, the preliminary stage, as being the stage in which a new theory or paradigm, if you like, to use the language of Thomas Kuhn, is formulated precisely. And by precisely there, they have in mind a mathematical formulation. That's the first step. Stages 2 and 3 are where we apply the mathematical theory to actual real-world phenomena. And in stages 2 and 3, we're mainly applying it to already known phenomena that already have, may have non-scientifically rigorous, non-mathematically rigorous explanations. And in stage 4, ultimate stage, we use the theory or research program to predict new phenomena, unknown or novel facts, and that's where the theory is really properly tested and corroborated. Okay, so in the previous lecture, Robert discussed these stages in general. Today I'll be talking about whether and how game theory has gone through these or has realised these particular stages in the decades since von Neumann and Morgenstern's book. Different ways in which these stages may have been traversed in the decades since. Okay, so let's start with the preliminary stage. So this is the stage of transition from pre-mathematical observation and reasoning to a mathematically rigorous theory. So we might have a series of disparate, more or less disconnected facts and phenomena which aren't connected and unified within a general theoretical framework formulated mathematically. And what we want to do is to move from that stage to a stage where we have a mathematically rigorous theory. And so if the question is, where did game theory pass through this stage? Well, probably with the publication of this book itself, von Neumann and Morgenstern's book itself, probably more than anything exemplified this particular stage in the development of game theory, because that's exactly what they were doing in their book, and they didn't really claim to have achieved that much more in their book than make a start at in this preliminary stage. And what they did is they laid down the foundation of the mathematical theory of games, game theory, which then was later developed by others. So they did the important foundational work in establishing a mathematical theory that was mathematically rigorous and complete and consistent, which is what the preliminary stage is all about. So recall, in this stage there's a selection of certain problems that allow for clear mathematical formulation. And it's understood that this is not the stage at which all the problems in this particular area or domain can be solved. Rather, a small number of problems which are simple, clear enough to allow for mathematical formulation and treatment are selected, and that's precisely what they did. As we know, as we've seen, they concentrated on one particular problem that could be formulated in this way, the problem of the interdependency of rational choices in interactive situations, which, as we've seen, really defines the research program of game theory. That was the problem. That was the problematic. That defined the problematic of game theory. That was the problem. That's not the only problem in when it comes to social phenomena and phenomena that economics attempts to provide explanations for, but that was the problem that could be isolated, that was clear, unambiguous, precise enough to be isolated and to be approached, to be attacked using the tools of mathematical analysis. So that's why they chose that problem, and the thought was if they could solve that problem or address it using these mathematical tools, that could provide a foundation for then the further development of the theory into other areas. So the question really was, how should utility maximizers behave in an interactive situation? That is, in a situation where the outcome depends not just on each individual agent's choice, but is determined by the set of all agents' choices. Okay, so that was the problem that they isolated. Now recall, in the preliminary stage, we must divide the difficulties. What does that mean? Well, that means in focusing on one thing or one particular problem or set of problems, we must downplay other difficulties in order to get at the heart of this one thing. We must, in a sense, bracket complicating factors that, of course, you would need to consider in order to give a complete picture of the phenomena of interest, but that for now they can be kind of bracketed, as it were, in order to focus and to isolate and focus on one particular problem that can be attacked. And this is a common approach and an indispensable approach in science generally. Scientists will focus on one particular factor or set of factors and sort of abstract from other complicating factors that later will be brought back in, ideally, to give a complete explanation, complete picture of what's going on. But the first stage, you need to simplify in order to make progress. There's a kind of trade-off between simplicity and accuracy. The more accurate a scientific model is, the more complex it will be, the more true it is to the world, the less simple it'll be. The more that you abstract, the more you focus on some small set of problems while kind of treating the rest as background or bracketing them off, the simpler your model will be, the more more progress you can make, presumably, but the less accurate it will be, because it's going to be excluding or bracketing a whole series of important factors that are required to be taken into account in any complete explanation of the situation. Okay, so famously, Newton bracketed wind resistance when formulating his and applying his laws of motion, and using those laws of motion to derive certain results with respect to the motion of bodies. And so he abstracted from the reality of the situation in order to give a simple and powerful, develop a simple and powerful model. Okay, and von Neumann and Morgenstern bracketed a whole number of complicating factors. I won't go into them. There's a list, non-exhaustive list of some of them in the relevant section of the topic notes, and you can have a look. And so they just focused on situations where you have a series of rational actors, interactive situation where the rational choice to make for any particular actor depends on what the other actors are choosing to do, and made idealizing assumptions as to the rationality and complete epistemic situation, so the complete knowledge of the situation on the part of all of the agents and so forth. Made these idealizing assumptions that aren't realized in reality, and abstracted from complicating factors, which was necessary. Okay. So the outcome of the preliminary stage was the development of the mathematical theory of games. The theory treats various classes of interactive situations, and for every class it seeks a solution. That is, a general rule of rational behaviour for the idealized agents who meet certain assumptions. Okay, and so then this was the achievement of the preliminary stage and the achievement of von Neumann and Morgenstern's book. They had a mathematical theory that was mathematically rigorous. Now this is of course only the preliminary stage. Just a moment. The point of the theory, after all, is to offer explanations of real-world social and economic phenomena. So the mathematical formulation of the mathematical theory is just preliminary to that. We want the theory to go on and do more. But you may wonder, well, what if it's not able to do that? What if it fails at stages 2, 3, or 4? Does that mean that what's been achieved at the preliminary stage is worthless? Well, as we suggest in the topic notes, the answer is clearly no. It's not worthless. The theory at this stage, even just understood as a mathematical structure, has intrinsic value. Firstly, it does deliver truths of a certain kind, mathematical truths, if you like, or conditional truths. If such and such conditions are satisfied, such and such outcomes will ensue, will result. And such conditional truths, of course, in order to get the truth of the consequent, the antecedent of the conditional needs to obtain. And, but nonetheless, these are conditional truths that the theory is able to deliver. And so it has cognitive value in that sense. But secondly, as a mathematical structure, the theory has a kind of beauty or elegance that mathematical theories have, if they work as mathematical theories. So there are a couple of analogies we may draw. So think of geometry as a mathematical structure. Euclidean geometry is a beautiful, elegant mathematical structure. There are alternative geometries such as non-Euclidean geometries such as Riemannian geometry and so on. They are mathematical structures which have a kind of aesthetic beauty. Then the question is, do they apply to time and space? Do they apply to the real world? Of course, for many years it was assumed that Euclidean geometry did apply to space. Space and time of our world was Euclidean. Since Einstein, it's been thought that's not the case. Space is actually non-Euclidean because of curved space-time and so on. But whether our space and time of our world is Euclidean or not, that is the question of which, whatever the answer is to the question of which geometry is instantiated by our world, it's still the case that as mathematical structures, Euclidean geometry, the other alternative geometries that are developed, have a kind of mathematical beauty in and of themselves. Okay. Another analogy might be with various logics. Logical systems are developed by logicians, by mathematicians, which again have a kind of intrinsic aesthetic elegance and beauty at their best. And then it's a further question, which logics actually underlie real world, real life patterns of inferences, whether in natural language or in mathematical or scientific reasoning or some other domain. And that's a question of the application of a theory. But whatever we say about that, the theories themselves have a kind of intrinsic intrinsic interest and value and beauty as mathematical structures. Okay, but still, we would like, ideally, a theory to go beyond just that stage and show its worth in being applicable to real-life phenomena, and that's what ideally happens at stages 2 and 3. We aim for a gain in our understanding and predictive ability as regards real-world social phenomena to be derived from our use of the theory as a tool of analysis. So stages 2 and 3 are the stages of corroborating applications and the stage of more advanced applications. So recall that in stage 2, and I'll be pretty much discussing stages 2 and 3 together. In stage 2, the theory is applied to a range of simple problems whose explanations are well known without any theory whatsoever. Okay, so we've got simple problems that have the intuitive or untheoretical explanations, and we take those problems, we apply our newly developed mathematical theory to these problems, and we check if there's a concordance between the known results that were achieved without the use of this theory we've just developed and those yielded by the theory. And if there is such a concordance, if the theory fits, if it gives us the right results with respect to, or at least results that fit with established results in these areas, then that can go some way towards corroborating the theory. Even if the results are already known, the fact that all of them have now been derived from the theory, that the theory is able to accommodate those results and fit them into its particular mathematical formulation, its particular mathematical form of explanation, we get a unified explanation for a whole series of prima facie disparate facts. This can help to corroborate the theory. Just one moment. Okay, sorry. Okay, and so we have a couple of analogies here. So think of stage 2 in the development of Newtonian physics. So the movement of the planets had been known and roughly calculated long before Newton developed his theory and applied his theory to celestial mechanics. But the fact that the theory was able to account for and accommodate the phenomena and the known facts about the movement of the planets was support for the theory. Okay, the theory, there was concordance between the results of the theory, what you can derive from the theory about the what you would expect to find with respect to the movement of the planets. There was a concordance between that and the known facts about the movement of the planets. Was strong support for the theory. In biology, the facts of biogeography, so the distribution of plants and animals around the globe, were well known before Darwin's theory of evolution provided a unified explanation for them. The pattern, the distribution of different types of organisms around the world were established. And then Darwin gave a kind of general, unified explanation for them. The facts are already known, but the fact that the facts were consistent with and expectations of or predictions of Darwin's theory, so the theory was in accordance with, fitted with the known and established facts about biogeography and of course many other things, was strong support for the theory, helped to corroborate the theory. So for instance, it was known before Darwin's theory was developed that all the large native mammals in Australia were marsupials. That was a known fact of biogeography. It didn't really have a good explanation before Darwin came along, but it was the sort of thing that you entirely expect given Darwin's theory. Straightforward evolutionary explanation, they're all marsupials because they all descend from a common marsupial ancestor. First mammals in Australia were were marsupials, and over millions of years they evolved, radiated, evolved into a whole number of different species occupying different niches, but they all continued, of course, to be marsupials and all derived from that original common ancestor. Okay, so that's the sort of thing that goes on in stage 2, the stage of corroborating applications. Stage 3 is a stage of more advanced applications. In this stage, the theory is applied to somewhat more complicated situations. The results obtained are in some degree novel and non-obvious. So rather than just offering explanations for simple phenomena, with simple problems, we have the application of the theory to more complex situations. Okay. So the question then is, how has game theory fared in these stages? Well, arguably it's been quite successful in stages 2 and 3. What we're looking for in these stages is a game theoretical vindication of our common sense intuitions. Okay, so we have common sense intuitions about certain classes of phenomena, certain situations, and we're giving a kind of game theoretical, mathematical explanation of what's going on in those cases, and it's going to hopefully vindicate our common sense intuitions. One example is prisoner's dilemma type situations. Now, topic 4 of the course, as you know, is all about the prisoner's dilemma. So we're going to be talking at length about the prisoner's dilemma shortly. But for now, I'll just briefly mention it as one example of what I'm talking about. So consider standing up at sporting events. Now, why do people stand up at sporting events? After all, if everybody's standing up, then nobody has a better view than if everyone was sitting down. Right? You're just as well off or just as bad off if everyone's standing up as if everyone's sitting down. And indeed, you're worse off because you're standing, which takes more effort, not as comfortable as if you're sitting. But there's a kind of rationality to the situation that's kind of intuitive, because if nobody else is standing up, then you get a better view by standing up. So you as an individual ought to stand up if no one else is standing up, because you get the best view. That's individually rational. What if others are standing up? Well, then what ought you to do? Well, then you better stand up too, because if you sit and everyone else is standing, you won't be able to see at all with people standing in front of you. So if everyone else is standing, you better stand too. So whether others are sitting or others are standing, the individually rational thing for you to do, it seems, is to stand. Whatever other people are doing, that's going to give you the best result. But of course, everybody reasons in the same way, so everybody stands up, which leaves everybody worse off than if everybody was sitting down. Nobody's seeing any better than if everyone was sitting down, and everyone's worse off because they're having to stand now. So that general, that sort of non-mathematical, non-theoretical description of the situation is well known. Okay, I've just described it in non-rigorous, non-mathematical terms, and we can see what's going on intuitively with the rationality of the situation. Game theory has the tools to give a precise mathematical explanation of what's going on in such situations. Firstly, in the particular situation of standing up at sporting events, or standing up at any kind of event where there are spectators. So it can explain what's going on in terms of the rationality of why people stand up. I mean, everyone's worse off. Why doesn't everyone just sit down? They're all worse off if they're all standing up. Well, we can understand it as I explained it in terms of what seems to be individually rational. We can do that in non-mathematical terms. Game theory vindicates those intuitions by giving a mathematical account of them. But more than this, I mean, if it was only able to kind of vindicate intuitions about these individual types of cases, like standing up at sporting events, it would be not so interesting. But what it's able to do is assimilate such cases to general types of phenomena, general classes of phenomena. thus allowing a deeper understanding. So it turns out, and again we'll talk about this more when we get onto the prisoner's dilemma, that standing up at sporting events in that situation is just one type, or one case of a general class of cases known as prisoner's dilemma cases, and I'll explain why it's called prisoner's dilemma when we get on to topic 4. And it turns out that these classes, that the members of this class have important features in common with respect to the rationality of individual behaviour. They're examples of the type of interactive situations that game theory was designed to account for and explain. And so what game theory is able to do then is bring out the crucial features of certain types of social phenomena that makes it the case that they are the same type, fundamentally the same type of phenomena as these other members of this class, and thus provide a deeper understanding. Okay. Relatedly, another achievement at stages 2 and 3 is game theory's typology of social interaction phenomena. So they show that social interaction phenomena fall into one or other general category based on certain features. This is the point I've just been making. They provide a kind of method giving a taxonomy or classification scheme of social phenomena. It's going to turn out that the problem of why people stand up at sporting events is structurally the same problem as the problem of why advertising companies spend so much money on advertising, of why nations engage in expensive arms build-ups. The irrationality of arms races, turns out, has the same kind of fundamental structural features as standing up at sporting events, the rationality of that in the sense of situations. They're all situations where by doing what seems to be individually rational, a set of individuals ends up in a situation where they're all collectively worse off. By pursuing their own individual rational interests, they all end up kind of collectively worse off. And so what's individually rational to do turns out to be bad collectively for the group, and everyone ends up worse off, even though they're all pursuing what is the rational course for them as individuals. And that's the kind of paradox and trap that we'll talk about with respect to the prisoner's dilemma. But what game theory is able to do is bring together and classify together such social phenomena, and that's one of its great achievements, not just with respect to prisoner's dilemma type cases, but other types of cases as well. And it does this through dividing social phenomena, social interaction phenomena, into one or other category on the basis of the following features of the situation, on the basis of how we answer the following questions about the features of the situation for that particular type of phenomenon. Firstly, how many players participate in the situation? Secondly, what is a set of strategies for each of them? Thirdly, are binding agreements on the choice of strategies possible? Fourthly, for any possible combination of strategies, what are the respective payoffs resulting from the player's choice in these strategies? Fifthly, what do the players know about the situation? And sixthly, what is common knowledge between them? Okay, so social interaction phenomena are put into one or other category by game theory on the basis of how we answer these questions for each of them. Okay, so that's enough about stages 2 and 3. What about stage 4? So this is the stage of prediction. So recall that in stage 4, the theory produces correct and previously unavailable predictions of quite complicated situations. So here's where we're moving from accounting for or explaining known phenomena to predicting previously unknown phenomena. So recall, Newton's theory was, of course, used both to explain already known facts, such as the movement of the planets, and to predict novel facts, make predictions about facts that weren't known. So one of the most famous corroborations of the theory, one of the most famous triumphs of the theory, was the prediction by Newtonian scientists of the return of Halley's Comet. Used the theory to predict the motion of the path of Halley's Comet, used Newton's theory to predict that Halley's Comet would be returning, coming close to the Earth at a particular point, and that prediction, that was certainly not a known fact, that was an unknown fact. It was a novel fact, novel prediction, and that prediction was confirmed, thus providing even stronger support for the theory than the previous types of corroborations that belong to stages 2 and 3. And there's kind of in the background here, a general issue in the philosophy of science about the difference between prediction and explanation when it comes to the corroboration of the theory or the test of the theory. Because the prediction of novel facts is often seen as the biggest test of a theory. And if such predictions are successful, they're often seen as providing stronger support for the theory than the explanation of known facts, right? So if a theory is able to make novel predictions that are then confirmed, that's seen as a bigger test, as giving stronger support, stronger confirmation of the theory than if the theory is able to explain facts that are already known about. There's a problem with the asymmetry of prediction and explanation, and I mean this is intuitive. It is intuitive that the fact that Newton's theory was able to predict startling facts like the return of Halley's Comet seems to be more support in its favour, better evidence in its favour than just accounting for facts that were already known. But this has been questioned by some philosophers of science who say, well, this is a bit puzzling, this idea of the asymmetry here, because, really what you have fundamentally is a theory and then a set of evidence. And the question is whether the evidence, to what degree the evidence supports the theory. Now, if the evidence is already known to us, we call that type of support, we say what's going on there is an explanation. If the evidence isn't yet known to us, then we say what's going on is prediction. But how can the question of whether we know about the evidence or not, if you like, where we stand temporarily with respect to that evidence, whether it's in the future, as with the prediction, or in the past, with respect to an explanation, how can that fact, which is just after all a fact about our knowledge, have any bearing on the question of whether and to what extent that set of evidence supports or corroborates the theory? And that's just a question of the logical relationship between the evidence and the theory, whether we already know about the evidence or not, and whether the evidence is a novel prediction or an explanation for known facts. That shouldn't, according to these philosophers, have any impact on, shouldn't be at all relevant to the extent to which the evidence is related to the theory. And yet it's very intuitive that when theories predict novel facts, that's more impressive, that provides more support for them than just explaining known ones. And so this was explained by Karl Popper when he talked about the importance of novel facts and so on in the corroboration of theories, and he talked about the importance of risky predictions. So what makes a good scientific theory, he thought, was a theory that makes risky predictions of novel facts that are not just novel, not just unknown, but risky in the sense that they clash with common sense and or established theory. And so the paradigm example of this that Popper talked about was the test of general relativity. The theory made a prediction. It was a very risky prediction. It predicted that light would bend around around the sun due to the curvature of space-time. This was a prediction that was a novel prediction. It was risky in the sense that it clashed with prevailing orthodoxy in physics. That's why it was seen as such a crucial test between the new Einsteinian physics and the old Newtonian physics. And there's this famous experiment done that had, well, the press knew about it, and it's one of the most famous experiments of the 20th century that still provides, one of the strongest pieces of evidence supporting general relativity, where this test was done to try and observe whether the light from a star would bend around the sun as predicted by general relativity, and it was stunning confirmation of the theory. Okay, this is a risky prediction that, when it was confirmed, provided very strong support to general relativity, and more so than its ability to account for already known facts. Okay, so that was just a bit of a digression on the relationship between prediction and explanation in the testing of scientific theories. But anyway, back to game theory. So stage 4 is the stage of prediction. So has game theory had any stunning successes comparable to the prediction of Halley's return of Halley's comet, Newtonian physics, or general relativity predicting novel facts? And the answer is really no. Game theory hasn't been as successful in stage 4 as it had in stages 2 and 3. It hasn't generated the kind of precise and accurate predictions of novel facts, as Robert discussed last time. But this shouldn't really surprise us, because the fact is social phenomena are much more complicated than natural phenomena such as the movement of the planets. For general reasons such as the fact that we're talking about human beings. Human beings are very complicated. They have minds, they have intentions, which are notoriously difficult to which make theorizing about human behavior much more complex and difficult than theorizing about the behavior of inanimate objects such as planets and stars and so on. So that's just why social theory, social science, economics, and so on, much more complex, difficult, messy, hard to come up with laws, strict laws, the way that the hard sciences such as physics and chemistry can. So this isn't really this isn't a special problem for game theory. This is a problem for all theories in social science. But nonetheless, game theory aspires to be a science and a scientific research program comparable, as I said before, to successful research programs in physics and chemistry and so on. So, that's what it's aiming to do. But as I said, the successes at this stage are much less impressive than with the previous stages. Of course, that doesn't mean that the theory is a complete failure, partly because it has achieved a lot at the early stages, and it's certainly not the case that, and von Neumann and Morgenstern weren't saying that unless a theory achieves great success at all 4 stages, it's completely worthless. We even said even if it doesn't get past the preliminary stage, it's not completely worthless. And in achieving what it has in stages 2 and 3, even the fact that it hasn't been able to generate many successful predictions of social phenomena, that doesn't mean that the theory isn't of great value and isn't a successful theory in its domain. And also, as I said here, it's not a special problem for game theory that it hasn't been able to generate these kind of predictions. That's the case, really, for all theories and research programs in economics and the social sciences generally. Okay, thanks very much. So that was part 2 of lecture 8, week 8. In the last 3 weeks, weeks 9, 10, and 11, we'll be turning to topic 4 of the unit, which is on prisoner's dilemma that I started talking a bit about today. We'll be talking about that at greater length. I will upload the week 9 lecture as soon as I can. I may not get a chance to do it this week. Actually, during week 9, I might have to do it during the Christmas break. Okay.